All right, so after some time looking at this, how many valence electrons do we have to work with? 17. Now, right away, you know, we should be a little bit anxious here, right? Because, yeah, it's an odd number of electrons. So there's no way we're going to come up with a structure that's going to have all the electrons paired up, right? So right away, that's going to be kind of a problem. But we go through our rules. So pair for each bond, make these guys happy. And then the electrons are left over, put them where? Central atom. Yeah, ideally in pairs, but in this case we don't have it in pairs. So what are we going to do? Well, first of all, we've got to get the nitrogen at least a little bit happier, right? Because right now, how many electrons are around nitrogen? 5. So we can make it a little happier by putting a double bond here, right? Do we want to do a double bond on the other side too?
No, because that would be 9.
Right, and nitrogen cannot go over 8, right? The second period elements, the carbon, boron, nitrogen, oxygen, fluorine, they cannot go over 8 electrons around them, right? So we can't do that, but we can have a resonance structure with this. Right, so those would be both resonance structures. So this is an odd electron situation. Doesn't happen very often, but in this case it does occur. This is the gas that, remember the demonstration that I did for the exam? Right, there's that brown gas that was given off. Right, most of you are like, nitrogen gas is a product of this reaction. Why is it brown? Well, that brown gas was actually this. Okay. Now, do you suppose this likes having an odd number of electrons? No. As a matter of fact, that odd number of electrons forms what are called radicals. Right? Radicals are very bad, right? Because they're very reactive. They don't like having odd numbers of electrons. Right? So those get inside your body, and immediately they start reacting with things to try and get another electron.
Like free radicals? Free radicals.
Free radicals, yeah. Right? Now, so what do you, I mean, you oftentimes hear like health benefits of antioxidants. Good. Antioxidants help reduce the number of free radicals in your body. And you can get them from green tea. They say you can get it from red wine, but you can get it from grape juice too. So don't feel like you have to go out and drink wine to get radicals or antioxidants. Blueberries? Maybe blueberries. I hadn't heard blueberries before, but that's possible. Yeah. Right. So these things, if they get into your body, they kind of create chemical reactions that you don't necessarily want to have happen in your body. So now the other thing that happens with these is if I put 2 of them together, maybe you can kind of guess what could go on here. Right, so if I put 2 of these molecules together, what do you suppose might happen? Yeah, they come together. I mean, look, this one's got an odd number of electrons. This one does. Well, let's take our electrons together and bond them together. This is what's called a dimer. Where you put those 2 together, and so the dimer, the formula for this dimer would be N2O4. You could do it with 2 different radicals, yeah. You could do it with 2 different radicals. Okay. Now, in the gaseous state, these things have enough energy that they just kind of stay apart. And so it's just the NO2, and again, very reactive. So you want to stay away from it. But when it goes to the more of a colder state, if you lower the temperature down and to where it's close to a liquid or even in a liquid state, that's where you get these molecules coming together and forming the dimers. Okay. All right. Good. Okay, so one more. SCN. All right, so give this one a try and see what you come up with. In something like SCN, the way the elements are listed is the way you want to put them together. So you want to have an S and a C and an N, like that. All right, so when you do the dot structure, you want to have them in that order. So let's see, sulfur 6, carbon's 4, nitrogen is 5, so 10, 15 plus 1, so 16 electrons?
Yep.
Right. So there's 16 electrons to work with. We do a pair for each bond. Good host rule. Oh, we got about Francesco's rule. So now we put in all of the electrons. Right? So what seems obvious here is to make double bonds on each side. Okay? Right. Now, is there another way that you could potentially do this structure, however? Good. Good. We could do this. Or what? Yeah. Nice, that was good. All right. So all three of these would be resonance structures.
All three?
All three of them would be resonance structures. Right? However, these are non-equivalent. Non-equivalent, which means they're different. Each one is different from the other ones in terms of, yeah, whereas remember when we did the one for NO3 minus, you know, each resonance structure was basically the same thing, just moving the double bond to a different oxygen. Here, you know, we have some triple bonds, and so what this is doing is it's showing that, you know, the electron density is more on one atom than another. Right? So where are we putting, in this bottom one, where are we putting most of the electron density? Well, I mean, which element, which atom of which element is getting most of the electron density? Sulfur, yeah. So in this one, the sulfur is getting most of the electron density. What about the one that's up from that? Which one gets most of the electron density there? Nitrogen. All right, and then in the top one? And there, it's a little more evenly distributed, right? The copper, not copper, the carbon gets basically the same amount of electron density in all of these, right? I mean, it ends up sharing 8 electrons in all of the cases, right? Sometimes it's a double bond on each side, sometimes a single bond and a triple bond, but it's basically sharing 8 electrons, 8 electrons worth of density, right? So it doesn't go either way. The question would be, which one should get more electron density, and should it get that much electron density? Yeah.
Sulfur, because it has more pull, right?
All right, good. Right idea. Which is going to have the higher electronegativity? Yeah, we'd want to use that to help us analyze the situation. So if we look at a periodic table, do I have one up here? We have sulfur 2.5, nitrogen 3.0. So nitrogen has a greater pull, so we'd probably think that the nitrogen would have, where'd it go? Yeah, so that would mean like this one might be our best in terms of more electron density on the nitrogen.
Wait, wouldn't that be the bottom one? Like the best choice?
Well, this one has more electron density on nitrogen, which has a higher electronegativity. right? So higher electronegativity means nitrogen should have more of the electron density, right? Do we want to have more electron density in sulfur? You know, not over nitrogen, right? But this one has kind of a balance, right? So maybe that one's better, right? Well, the answer here is looking at something called formal charge. And I'm not going to ask you guys to do this for these, but just so that you can kind of be aware of it if you do honors chemistry next year or AP chemistry next year or something else, you know, we have to deal with it. Formal charge is something that you figure out based on, you know, what each atom is getting out of this deal. So for instance, the sulfur, how many electrons did sulfur come in with when it made this bond up? Had 6, right? How many does it have now? No. It has 4 by itself, and it's sharing 4. So the shared ones only gets half. So it came in with 6, and now it's got 6, so it's got a formal charge of 0. Right? Carbon came in with how many? 4. How many does it have now?
Well, it has none. It's sharing.
Yeah, it's sharing 8, so it's got 4. Right? Nitrogen came in with 5, and now it has
5.
6. It's got 4 by itself, and it's sharing 4, so it gets half of those. So the formal charge on nitrogen is at 1 minus, because it has 1 more electron worth of density around it. That seem to make sense?
Yes.
Right? All right. Now, in the bottom, this one here, just real quickly, you'd find out that the nitrogen here has a 2 minus, and the sulfur ends up with a 1 plus. Carbon is 0. We tend to not like having large formal charges. So the one that has a smaller formal charge is actually the best here. So the top one works out to be the best one here. Okay. Again, formal charges, just wanted to let you see it, but it won't be on any of your quizzes or tests. Right? So you don't have to worry about that. All right. But we do have a quiz tomorrow. It'll be on the mostly bonding stuff, but we'll put a couple of light dot structures, kind of like the worksheet on there. Okay. All right, and no resonance on tomorrow's.